Why are deadlocks so hard to reproduce in debugging? Have you ever faced a situation where your program just hangs and you can't seem to figure out why? This often leads to a frustrating deadlock. But why are these deadlocks so tricky to reproduce during debugging? Let's break it down. Deadlocks occur when two or more threads are waiting for resources held by each other. Imagine two cars at a one-lane bridge, each waiting for the other to move. This situation requires a specific sequence of events to happen, which is often rare. The timing and order of how threads interact with shared resources can change every time the program runs. This variability makes deadlocks appear randomly and unpredictably. When you are debugging, you might use breakpoints to pause the program. However, this can disrupt the timing of the threads. If one thread is paused, it may prevent other threads from reaching the state that causes the deadlock. As a result, the deadlock might not show up during your debugging session, making it seem like the issue has vanished. Another challenge is that deadlocks can involve many threads and locks. In a program with numerous concurrent routines, the backtraces showing which threads are blocked can be extremely long and complex. This makes it difficult to trace the root cause of the deadlock quickly. To tackle these challenges, consider using non-intrusive debugging techniques. Instead of breakpoints, you can use tracepoints or logging. These methods allow the program to run without pausing threads, which helps maintain the natural timing and increases the chances of reproducing the deadlock. Monitoring how locks are acquired and how resources are used can also help. By keeping an eye on these patterns, you can detect potential deadlock situations before they happen. Additionally, using specialized tools or building simple deadlock detectors can be beneficial. These tools track which threads hold or wait for which locks, helping you identify cycles in resource dependencies. Understanding the locking protocols and fairness policies of the synchronization methods you use is also important. Sometimes, subtle behaviors can lead to deadlock situations, even when everything seems logically sound. By mastering these techniques, you can improve your ability to reproduce, detect, and fix deadlocks in your software. Remember, deadlocks are sensitive to timing and thread scheduling. Designing your debugging strategies to minimize interference with the program's natural flow will make these bugs easier to diagnose and resolve.